Hello and welcome to my Lab 3 presentation. Today I'm going to be presenting to you the Floyd Warshall algorithm, and I thought this would be an interesting topic because it combines a few of the last topics we discussed in class towards the end. So in the style of Nick Painter, I'm going to go ahead and present you with some motivation and then some definitions and then an example. So we have seen applications of graphs and paths in class. We discussed GPS systems and networking and routing, but you're probably using your GPS to get you from point A to B and then back from point B to A and then maybe from point C to D. So if we would want to find the shortest path between every pair of vertices in a graph, we saw that we could run Dijkstra's algorithm, but Dijkstra's algorithm works from a single source vertex, so you would have to rerun the algorithm on every single vertex of the graph. Instead, we could use a dynamic programming approach, which would reduce our runtime, which is where Floyd Warshall gets introduced. So this is a dynamic programming algorithm which finds the shortest path between all pairs of vertices on a weighted directed graph. And it does this by iteratively checking each node and checking to see if that node can serve as an intermediate node between two other nodes to shorten the path. It stores this information in matrices, or you could do a 2D array, and this brings the runtime to find every single shortest path possible in n of cube time. So we're going to go ahead and do an example, and then I'm going to show you how we would use our final matrices to find a path. So here I showed you the initialization of the initial matrices. This matrix MO is going to store the current distance between nodes, and T of O is going to store intermediate nodes within that shortest path distance. And this goes to and from to make it less confusing. So you can go ahead and check my work, but I filled these in for us. So we're going to go ahead and start with the first iteration. In the first iteration, we're going to check, can vertex A serve as an intermediate node to shorten any paths within our graph? So I kept all the rows that are going from A and then to A. So we're going to go ahead and do the math on every other node. So from node B to C, current distance is infinity. So we're going to check with A. From B to A, also infinity. A to C is distance of 2. 8 plus 2 is greater than infinity. Infinity plus 2 is greater than infinity, so we don't update. Okay. B to D currently is at 1. B to A is infinity. Infinity is greater than 1, so we don't update. And what about from C to B? Currently the distance is 6. If we go C to A, distance is 3, A to B gives a distance of 2, and actually 3 plus 2 is less than 6, so we do update via A. So we will fill this distance in to be 5, and then the intermediate node is A. So from C to D, distance of infinity, C to A is 3, A to D is infinity, don't update. Oh, I'm so sorry, this was 8, but regardless, we don't update because 3 plus infinity is not less than 8. D to B is infinity, D to A is infinity, so we don't see any change, any shortening of the path. Then from D to C, we're currently at 4. From D to A is infinity. Infinity is not less than 4, so we wouldn't update here either. So we were able to get one path shortened, which is nice. And then you would go ahead and do this on every single vertex of the graph. I'm going to go ahead and show you my work really quickly, but we're not going to do it together. So this is for the second iteration. We see two nodes were actually, two paths were actually updated. And then for the third iteration, can vertex C serve as a node to make anything shorter? We see 2 more paths were updated. And on vertex D, it was able to shorten the path. shorten one path. So here we are brought up to our final matrices. These show the current shortest distances and any intermediate nodes to get to those shortest paths, to get from and around those shortest paths. So how would we find the shortest path from B to A? So starting at B, going to A, we'd go ahead and see that the cost is 8, so we know it's going to cost us 8. B to A is going to go via vertex D. Okay, now we're going to check from D to A. That's going to be via vertex C. Okay, we can check our math from B to D. B to D is 1. D to C is 4. C to A is 3. This does in fact equal 8. Nice. And another one we could do, what's the shortest path from C to B, right? From C to B, we can see we need to use vertex A. So we would go in C, A, B, and the total distance from C to B would be 5. From C to A, it's 3. And then from A to B, it's 2. So this, in fact, does equal 5. You would go ahead and update your implementation of the algorithm accordingly. I like using the matrices, and then the building of the path can also be done within the algorithm itself if you add some tweaks. I hope you enjoyed my presentation. Thank you so much for watching.